I hope you find this introduction to electricity enlightening. I remember as a child being amazed that electrical energy could be transmitted over large distances using just small wires. How was that possible, I used to think. Have you ever had similar thoughts and questions? Well, today we're going to discuss some basic electrical terms and relationships. The first term is charge, i.e. electrical charge, and it's symbolized by the letter Q. All matter can be broken down into individual units called atoms. The building blocks of the atoms are then composed of three types of particles, two of which have charge. So you see a representation of an atom at the right. It has three negatively charged particles called electrons around the outer part, and these are indicated by the red balls. Now, since this atom has three negative electrons, it normally would have three positively charged particles at the center called protons. Atoms can also then have uncharged particles in the center called neutrons. Neutrons are electrically neutral, hence their name. And an atom can have a variable number of neutrons. In this example, there's just one neutron at the center, and it's a purple ball with nothing inside of it. The unit of electrical charge in the SI, i.e. the International System, is called a coulomb, and it's symbolized with a capital C. It takes many electrons to make a coulomb of charge. Now, how are electrons, protons, and neutrons similar and dissimilar to each other? Well, electrons and protons are similar in that they both have the same amount of charge, but they are dissimilar in that their charges are opposite to each other. And even though electrons and protons have the same amount of charge, electrons have much less mass than protons. It turns out that protons are about 2,000 times more massive than electrons. Now, protons and neutrons are similar in that they exist in the same part of the atom, that is the center, and they have about the same amount of mass. But a significant difference is that protons have charge and neutrons don't. In essence, neutrons are protons, but without the charge. Now, by static electricity, we mean that there could be a buildup of charges, but they are not moving, hence the term static. When we use electricity practically, it's almost always with moving charges, so it's not really static electricity that you use in household applications. But anyway, we will discuss static electricity here briefly, and there's an important law called Coulomb's law. You can see right there at the bottom of the page. It tells us that there's a force between any two charges. The amount of force is given by a constant, symbolized by that K at the right, times the amount of one charge times the amount of the second charge divided by the distance between them squared. And now I hope you can see this relationship between force, amount of charge, and the separation distance between the charges is very similar in form to another relationship that we saw in an earlier chapter. Can you tell me what that other relationship is? And can you tell me how this relationship with charges is fundamentally different than that other relationship? A hint is found in the parenthetical statement at the very bottom. Let's briefly describe some other widely used electricity terms. First is current, symbolized with an I. Electrical current is the flow or the movement of electric charges. When charges move along a conducting material like a copper wire, we have an electric current. And the language is similar to water. We have a water current if water is flowing in a certain direction. The unit of electrical current is the ampere, called the amp for short, and symbolized by the capital A. Resistance is just what the word implies. It is something that tends to prevent or impede an electrical current. Resistance impedes the flow of electrical charges. It is analogous to putting something in the stream of water so that the water can still flow, but not as freely as before. The SI units of electrical resistance are called ohms, and they're symbolized by the capital Greek letter omega. Next is voltage. Electrical currents do not just spontaneously start. Voltage is the electrical energy that produces and maintains an electrical current. The units of voltage are, interestingly enough, volts. And finally, we see power symbolized by P. And just like in our discussion of mechanical work, energy, and power, electrical power is the rate at which electricity expends energy. Recall, it is the amount of energy divided by time taken to do it that gives us power. And as before, the units of power are watts, symbolized by the capital W. Now the diagram at the right with the water system is from our text, and it attempts to show a water analogy to the electrical terms that we've just reviewed. Water in the pipes, just sitting there, is like static electric charge. Water moving through the pipe is like an electrical current. The water wheel acts as a resistance. Now, to make sure you understand this, imagine how efficiently the water would flow through the right side if there was just one pipe connecting that whole right side and it bypassed the water wheel. It would flow much better. So it's apparent that the water wheel tends to resist the flow of water somewhat. It acts as a resistor. And finally, the pump is like the voltage. It is what drives the water through the pipes. Without that pump, there is no flow of water, i.e., there could be no current. Let's finish this introduction by looking at two important electricity relationships. To be sure, we will be using these in class, on homework, and in the next project set. First, Ohm's law, which gives a simple relationship between voltage, current, and resistance. The two equations on the second line really just say the same thing. If V equals I times R, that means I equals V divided by R, or R equals V divided by I. All three are essentially the same equation. They come from the same equation. Then second, there is the power law. Power equals current times voltage. Now recall, I is current in all these representations. Now there are two equations below the first line of the power law, and the first equation at the bottom comes by substituting V from Ohm's law, that is I times R, into the power equation. So we get I squared times R. And the last equation at the bottom comes from substituting the I, which equals V over R from Ohm's law, in for I in the power law. So you might want to just check that out a little bit and make sure you understand that and see how that works. Now you might also wonder, if there are three equations for power P, which one do I use? Well, the answer is simple. It depends on what is known and what is trying to be found. All three relationships are correct, but in a given situation, only one is likely to be helpful. Okay, thanks for hanging in there. We had to spend a little time going through these basics before moving on to some more interesting applications. I'll see you in class.